In this new unit of study, we were looking at the applications of derivatives. One of the most commonly used applications of derivatives is to find an extreme value of a function. So that's our goal in this lesson, how to use calculus to find extreme values such as minimums and maximums. Alright, so what are extreme values? So I had said that word minimum and maximum, and you might have an idea of what that means, but we are using the definition as like the highest point or the lowest point of a function. It may or may not be a relative min or maximum. The basis of what we're working on today is the extreme value theorem, and it says if a function is continuous over a closed interval, then it must have a minimum or maximum value on the interval. Well, why would this be true? Because some of us have a picture in our mind of what we maybe think of what a minimum or maximum is. So let's just go ahead and sketch out a couple of examples. So maybe what you picture when you think of as minimum and maximum is something like this. And so we do want to be on an interval. So maybe between here and here. And so we want the minimum and maximum to either be the high point or the low point. So you can see that here is a high point, so that would be the maximum. Here is a low point, that would be the minimum. So that's probably what you're most familiar with for when we talk about minimums or maximums. But what if we look at a graph that does not have a relative minimum or maximum? Something like a linear function. If we choose an interval, let's say from here to here, it doesn't have any relative minimums or maximums, but it does have a low point and it does have a high point. So this low point would be the minimum and this high point would be the maximum. The last kind of strange situation that we might encounter with this, just to make sure that we've covered the different possibilities for what might happen, would be if you have a constant function. And let's say we look at the interval from here to here. In this case, the minimum and maximum value are the same value. So that's probably one of the most unique situations that we'll look at today. Well, so how do we use calculus to help us with this? Whenever we're looking for relative mins or maxes, sometimes you think of them as hills or valleys. Those are places where the graph has a horizontal tangent. So that's where the derivative of the graph is equal to 0. Other mins and maxes might be at something called a critical number. So a critical number, a piece of vocabulary you need to know, are a place where the derivative is equal to 0 or does not exist. So what we're checking for mins and maxes is actually cusps and corners, because they behave an awful lot like relative mins or maxes. And they would occur where the first derivative equals 0 or is undefined. We know at a cusp or corner, the first derivative would be undefined. Well, what if a function doesn't have any relative mins or maxes or any cusps or corners? Then the endpoints might be where the highest or lowest point might be. So these are all the places that we have to check when asked to find the mins and maxes. Just to make sure that we're clear on what I mean by relative or local extrema, I'm going to go ahead and just sketch out just kind of maybe your more typical polynomial function. So we would refer to this as a relative max, and we would refer to this as a relative minimum. Sometimes they're also called a local minimum or maximums. Why they have this specific name is relative to the points around them, this happens to be a high point. Relative to the points around it, this happens to be the low point. There might not be the absolute min or max, but they could be. Just those are the ones that you're probably most familiar with, but something like this might also be a relative max, and something like this could also be a relative min. It's a high point in relation to the points around it. This is a low point in relation to the points around it. So just so that you have an idea of perhaps what to expect from different functions. All right, so then besides relative mins or maxes, we have two other labels for mins and max. They are absolute minimums or maximum. The absolute has a special meaning. or the absolute minimum, pardon me, has a special meaning. It is the smallest y value on f of x. So it's the absolute lowest point. Okay, there may be other relative minimums or low points on the graph, so they may be categorized as relative minimums. There might even be a point that you feel like might be labeled as both the absolute and the relative min. We'll talk about how we would do these labels in just a minute. The highest value on an interval, or the highest possible height, is referred to as the absolute maximum, and other high points on the graph might be categorized as relative mins or relative maximums. Okay. Just something to be aware of that may seem kind of common sense, but we'll go through some examples in a minute of why you just need to be careful. In order for there to actually be a high or low point, or for a key feature to be an absolute min or absolute max, it needs to actually be a point on the function. So if there's a hole at what appears to be the high point, that can't be the high point because there's no point there. Okay, so there's, for example purposes, kind of a strange looking graph has been shown just to try to illustrate some of these ideas. So let's try to categorize all these points A through G as what type of an extrema they would be. All right, so if we want to go ahead and look, if we start with A, there's a point at A, but it doesn't appear to be a low point at all, so it's probably going to be none. Okay. If I'm going ahead and I look at B, B appears to be the highest point on the interval. It also looks like a relative max, so you could either label it is for sure the absolute max. If you also chose to describe it as being the relative max as well, that's fine, but it is the absolute highest point on that interval. Well, if we look at C, that doesn't seem to be either a min or max, so I'm going to label that as none. If I go ahead and look at point D, it looks like it's going to be the lowest point for the function. But unfortunately, there isn't a point at D, so I'm going to have to label it as none. It doesn't get to be the absolute or relative min if there's no point there. Point E looks like a high point in this general vicinity, so it gets to be labeled as a relative max. Point F is a low point in this general vicinity, so it's labeled as a relative min. And G doesn't appear to be either. It's not a high point or a low point because we don't have other points on the other side of it, so it's none. Well, hold up. I thought the extreme value theorem says that a function must have an absolute max and an absolute min. Well, this one only appears to have an absolute max, but no absolute min. Well, I know we said F was a low point, but there are other points lower than F. But we can't really describe where those low points are because they're getting infinitely close to D, which does not exist. So remember that the extreme value theorem is only applicable for continuous functions, and this function right here is not continuous. Oops. All right, so let's just practice labeling critical numbers. So critical numbers in calculus is very important. Remember that those are places where the first derivative of the function is either equal to 0 or undefined. Okay, so if we go ahead and look at this one right here, appears to be a horizontal tangent right there, so there's a critical number at 2. Well, the function's also not differentiable here and here, but there's not actual points there, so they can't be critical numbers. All right, so on this one we have, it looks like there's a horizontal tangent here, here, and then here there's a corner or a cusp. So the first derivative would be 0 at 1. It would also be 0 at 3. And the first derivative is undefined at 2. So those are all the critical numbers of that function. Okay, well, we've looked at a couple of graphs, but how would you do this algebraically without perhaps starting with a graph of the function? So let's look at the polynomial f of x equals 3x to the fourth minus 4x cubed on the closed interval -1 to 2. So that if we want to find all of the extrema, this would mean make sure that you find the absolute mins and maxes as well. We want to start by finding the critical numbers. Okay. So go ahead and take the derivative. So we get 12x cubed minus 12x squared. We want to know where this is equal to 0 or undefined. This polynomial is not undefined anywhere, so I just am worried about where it's equal to 0. This is actually easily factorable. I start with GCF. I can take a 12x squared out of everything, leaving me with x minus 1. Okay, where does 12x squared equal to 0? That's at 0. Where is x minus 1 equal to 0? That's at 1. So now I want to check where the absolute highest and lowest points are. Remember, we care about the highest and lowest points on the original function. So now we want to check, are these the highest and lowest points? But the endpoints are also candidates for the highest and lowest points. So we go ahead and we want to actually check the heights at -1, at 2, at 0, and at 1. Okay, so you need to plug these back into the original function. So just as a quick reminder, there are some ways that you can speed that up. You're welcome. This one's not hard to plug in, but I had been using my graphing calculator to graph this function, so I have the original function in my y equals. Remember that you can use the ask feature on your table to quickly crunch some numbers. So I think some of the x values we were interested in were 0 was one of them, I believe, 1, -1, and 2. So that would be a quick way to generate those values. It's a common mistake for people to plug these in to the derivative, but recall that I care about high and low points on the original function, so please use the original function to generate these values. Okay, so we'll just put those over here so that we have them. So then going ahead to look at this, we would say that 16 appears to be the highest point, so this is the absolute max, and -1 is the lowest point, so this is my absolute min. It's okay to say the point that it referred to, but just so that you're aware, the 16 is what's being referred to as the absolute max, and the -1 it's being referred to as the absolute minimum. All right, so let's find the extrema on the interval from -1 to 2 for the linear function f of x equals 2 times 3 minus x. All right, so again, the process is identical for all of these problems. You want to find the critical numbers, and then you want to find the heights at the critical numbers and the endpoints of the function. Okay. So you might want to, perhaps distributing that 2 first would be helpful. So make this 6 minus 2x. Okay, so the derivative is just going to be -2. I want to know where that's equal to 0 or undefined. All right, well, -2 can never equal 0, and -2 is never undefined. It's always -2. So this has no critical numbers. That shouldn't surprise us. I wouldn't expect a linear function to have a relative minimum or maximum. So that means that I only would check the endpoints of my interval to see what those heights are going to be. So I plug in -1 up into the original function, and then I end up getting 8. I end up plugging 2 into the original function, I end up getting 2. So my absolute max is 8. And my absolute minimum is 2. All right, so let's look at another example. So this one has I've rewritten it as an exponent, but we're dealing with some radicals now. I just want to practice showing you how you would take the derivative and simplify these. We will be doing more simplifying than we've done in the past with derivatives since we are solving equations with them. So I start first by finding my critical numbers. So I go ahead and I take the derivative and I end up getting 2 minus, I bring down the 2/3 power, so the third and the 3 end up canceling, so minus 2x to the negative 1/3. I want to know where that's equal to 0 or undefined. Does not exist. I want to clean this up. I want to be able to solve this algebraically by hand. There will be some circumstances where you'll want to use technology to solve the equation, but you also need to be prepared for doing it without technology. So I would recommend some of these equations that are simpler to brush up on some of your solving skills. Okay, so the first thing I'm going to do is rewrite this in a way that might be helpful. Okay, so whenever I'm dealing with a rational function, I would want to get it all with one denominator. So this one here is going to need to be multiplied by the cube root of x over the cube root of x. That would give me 2 cube root of x minus 2 all over the cube root of x is equal to 0 or undefined still. Okay, whenever I'm dealing with a rational function, it can only equal 0 where the numerator equals 0. But it will be undefined where the denominator is equal to 0. So that's how we're going to get our critical numbers. Okay, so just on a side note, we'll take our numerator and set that equal to 0. So we bring the 2 to the other side, divide both sides by 2, cube both sides, and I end up getting a critical number of 1. Where's the denominator equal to 0? Well, where the cube root of x is equal to 0 is when x is equal to 0. All right, so now we have our list of values to check. I want to know what f of negative 1 is. I want to know what f of 3 is. I want to know what f of 1 is. I want to know what f of 0 is. So I plug all of these back into the original function. If you just want to take my word for it, where I get these values from, so if you had plugged in 0, you get 0. When you plug in 1, you get negative 1. When you plugged in negative 1, you get negative 5. And when you plugged in 3, you got negative 0.2403. Okay, so the highest value that we have this time is 0, so my absolute max is 0, and my absolute min is negative 5. I know that we were categorizing relative minimums and maximums as well, but we would need a sketch of the function or more information that we'll practice in later lessons to be able to tell if these are relative minimums or maximums or not. All we're concerned about right here is high points and low points. You would need more information to be able to put any other categorizations on. All right, so this one, you're not given the equation. They just want you to find the extrema of f on the interval 1 to 4. All right, so if we go ahead and take a look at this, I see that from 1 to 4 there's no relative mins or maximums. Okay, so the lowest point is going to have to be 2, and the highest point is going to have to be 5. So my absolute min, so my absolute min is 2, and my absolute max is 5. All right, so in this lesson we looked at categorizing what it means for something to be an extrema, a minimum or maximum. It just means high point or low point. It might mean the highest point or the lowest point, or even just a high or low point in its general vicinity. We talked about how using calculus to find critical values is one way to find the highest and lowest point, but also don't forget to check the endpoints of the interval.